Доброго вечора всім. У нас сьогодні незвична зустріч. Він зараз знаходиться в Чорногорії, Montenegro, I think.
Yeah, Montenegro.
Montenegro. Now Bill is in Montenegro. І сьогодні ми будемо вести нашу дискусію, нашу розмову англійською мовою. Тому от згадуйте англійську мову, слухайте гарну англійську мову, англійську термінологію. Це теж такий буде тренінг сьогодні. І я представлю Біла на українській, а потім вже перейдемо на англійську. І я пропоную вам задавати, якщо питання будуть по ходу виникати або в чат. Так, можете задавати українською, я буду намагатися, якщо що, перекладати, але не думаю, що це такий зручний варіант, краще все ж таки англійською. Біл, він сам американець, він народився в штаті Мічиган, тривалий час він проживав у Піттсбургу, потім переїхав до Техасу, а зараз він отримав постдок в Інституті математики Польської академії наук. І зараз він подорожує Балканами, іноді він приїжджає і до України. Я так розумію, що я бачила, може зараз Біл скаже про це більш детально, але я бачила його семінари в Інституті математики, в педагогічному університеті імені Драгоманова також є певні контакти, тому він тривалий час жив в Україні і от каже, що розуміє і трошки українську, і трошки російську. І сьогодні він буде розповідати нам про свій досвід, про свої задачі математичні, які він розв'язує, про дослідницькі задачі в математиці. Може, якщо ми можемо його запитати, якщо він розкаже про те, як влаштована система математична і дослідницьких якихось заходів в Америці, якщо у вас будуть запитання, але, можливо, він, власне, в своїй доповіді про це розкаже. Тому... shall we start? I present you, and I said that you was born in Michigan, am I right?
Yeah,
and then live
near Detroit, yeah.
Yes, and live in Pittsburgh, and then you moved to
Pittsburgh for
Texas.
undergrad. So undergrad was at Carnegie Mellon in Pittsburgh, so it's 4 years, and then Ohio State, and then postdoc in Texas. I more or less understood what you said. So.
Oh, great. So maybe we could start your presentation, your talk.
Sure. Yeah. So, and one of the things I just want to start out with is just really explaining the difference between math and science, because I think this is a really, really important point when we're talking about this. So just kind of the fundamental philosophical difference is, okay, in science, and we're going to include, biology, chemistry, physics, sociology, psychology, any of the ranges of things that could be under some umbrella of science. The basic problem is that there's possibly some fundamental rules that are operating, say, of the universe, like, taking physics as an example, because it's a little easier. In the sense, we think, we're not sure, we think there might be some theory of everything where if you know these rules, you can more or less describe what happens in the universe, but we don't have any idea what it really actually is. We have some idea, but we don't. So the idea is that you're making educated guesses, and that's not a bad thing at all when I say educated guesses, but you make some observations, you think something probably works this way, and then you formalize it, often in mathematical language, not always, but often. And then you do experiments to test this. And that's a key thing, that what your experiments tell you, they don't even tell you that what you said is correct, because there's room for experimental error, right? That you can do some test and then you statistically say, okay, what's the probability that this result was useless and the probability that it wasn't? And there are a lot of scientific papers that are completely not reproducible, that someone did some experiment and makes some claim, and then no one who does the same experiment gets the same result. There are some other experiments that are very easily reproducible and all kinds of levels in between. And what we're trying to do with science is getting more and more closer to what these base rules that are governing our system are doing. Am I speaking, by the way, just to make sure, because of the language difference, is this okay with my English right now?
So if okay, you maybe put plus in chat if you understand, or we could ask Bill to talk slowly.
Yeah. But if my speed's a problem, let me know.
Yeah, I will check chat and let you know.
All right. So anyway, so we're never going to actually even know for sure if something is correct. We can actually even guess on the right rule, and we might get more and more experimental evidence that suggests it's right. But think about, like, from the perspective of physics once again, that Newtonian mechanics works all nice and well, but then, like, you have high velocities or high gravities and things get kind of crazy, or maybe the scale gets too small, and then, well, maybe we want to go to quantum mechanics. And even if we get some sort of theory that we think describes this all, well, maybe there's some special case we didn't think of that where things go a little crazy. And the same thing is also applying to psychology as well. How does the brain work? How does this very, very complicated system operate?
So maybe a little bit slowly, because yes.
Okay, sure.
Thank you.
So in these situations, you can do research by doing an experiment. You don't have to do something that's of some fundamental nature. You can do some lab work, you can do some statistical test, you can collect data, and it can be insightful. Sometimes even an experiment that shows no results can be useful and interesting, right? That maybe there's a problem in the culture of science that there's often an expectation of some positive results. So people can kind of do some shady things when they do their research to try to make it look like there is an effect when there isn't. But from my perspective, at least, if you do an experiment and nothing interesting happens, that might actually be something interesting of itself. It says, okay, there's maybe nothing there going on. In math, we have a completely different situation, and the philosophy is totally different. So in math, what you do is you start with the rules. So in science, you don't know the rules. You're guessing at them. You're making better and better guesses. In math, you start with the rules, and then you see what you can logically infer from those rules. The problem is that a lot of the objects we're talking about are infinite. So if you want to make some claim about the integers, like 1, 2, 3, 4, 5, 6, and so on, say positive integers, there's infinitely many of them. So if you say write a computer program to test 1,000 of them or 1,000,000 of them, it doesn't actually tell you anything for sure. So if I'm trying to claim like this is true for all integers, then if you do experimental tests, then it can be called a conjecture. You might think that it's true, but you don't actually know it's true. So for something to count in math, you need a proof. Okay. And what is a proof? I don't know how much students have seen proofs in their classes, or what's the standard in Ukraine. I know for Olympiad it's needed, but I don't know what's
yes. I think in all our program we need to have a proof, and I think it's a difference from the American.
It depends on the school. There's a wide variation in the U.S., but generally I would say our mathematical education is pretty bad, except for some places where it's very, very good. So a proof is kind of the fundamental thing you need in math to check if something is true or not. And the advantage of this is that if you do correct mathematics, meaning you didn't make a mistake, people do make mistakes, it happens, but assuming you do correct mathematics, then your result is true. And no one's going to be able to later say that this doesn't work, it's not correct. You can do correct science, you can do an experiment, and you're never guaranteed that your result is correct. With some probability it's correct. And so that's one of the advantages there of doing math, but a disadvantage is that proofs are really, really, really hard, often. Not always, but very often they are. And what can happen is that you get a very big barrier to entry. So it's one of these types of things. You can imagine some task where, okay, maybe there's even some very skilled people in it, but it's very easy to get started. the problem with research in math is that there's kind of a, usually, not always, but usually a pretty big cliff you have to climb over before you really get started doing this activity. So the problem is, math is very, very old. If it's, you could say it's older than, many of the sciences, at least, I don't think that physics, for example, took like a really good form until, say, Newton, formalized Newtonian mechanics, for example. Math is quite a bit more ancient, and part of the problem easier already been done. And some of the things that are easier to do that can still be done are very abstract, and you need to learn a very large amount of math to do them. So this is where, say, doing research as a high school student is very difficult, and it's definitely doable. Like I've worked with, there was a 15-year-old I published a paper with in International Journal of Number Theory. 16-year-old I published a paper with in Advances in Math, which is one of the best math journals. But the key thing is that they published with me, not by themselves. So the most important thing, this is about how to find research problems. And by far the most important thing is to talk to someone who's an expert, to be social, to reach out to someone. And I know this may seem a little bit unusual to do, but the problem is that, if you don't have, just because you're younger and you haven't had time to accumulate enough knowledge, it's really, really hard to tell what is new or what's actually interesting or what's impossible to do. So I can give some examples of some problems that you can state really easily that you have zero chance of doing. So one of the famous problems that's been open for a few hundred years is called the Goldbach Conjecture. And I can, every even number is the sum of two prime numbers. So for example, maybe I can even type these in the chat to make it a little bit easier to see. So 4 is 2 plus 2. Okay, 2 and 2 are prime. 6 is 3 plus 3. 8 is 5 plus 3. 10 is 5 plus 5. And so on and so on. Okay. And last I checked, this is as of July, I think, people have run a computer program to test this up to like 4 times, I think, 10 to the 18th, I believe. So this is a very big number. And so some supercomputer probably ran through on some clever algorithm that found some way to express all the even numbers up to this point as a sum of two prime numbers. Is this true, in general? Maybe there's some counterexample, maybe around 10 to the 600. There's some even number that is not the sum of two primes. Nobody knows. The problem with something like this is that it's so easy to state that if it was something we knew how to do, someone would have done it already. So first thing I definitely want to recommend is not to try some problem like this. Some sort of very difficult, hundreds of years old open problem that's easy to state. It's a trap. You're not going to get anywhere on it, and this is, I think, something where, I remember being myself a very energetic high school student. I had no guidance and no one to talk to, and I would try things like this, and it just kind of wasted my time. I mean, I think if you want to think about something like this for an hour or two just for fun, then it can be useful, but any more than that, there's no point. So what comes down to, what are reasonable things you can do? Well, one thing I do want to also mention that when you're younger and haven't seen as much stuff, it's very, very, very common to reprove results that are already known to be true. So I think most, let's say most mathematicians that knew they liked math when they were younger, that's not everybody. Some people find this out later in life, but I think most mathematicians who were energetic about this when they were younger, they try playing around and guessing at something and proving something, and then they end up just being disappointed later when they found out, okay, this is something that's everybody already knows except for me. And everybody, not meaning like all your friends at high school, but that means, kind of mathematicians. Or maybe you find it in some class when you're a university student. So this is a very, very common thing. And this is where, it also depends on what the standards of this, high school research thing are. I think actually expecting something of any real significance kind of forces a few certain areas to look at. So there can be problems coming from applied math, which, would also include computer science. So I don't know how common it is to know some amount of programming here. Like there's a little bit of a ambiguity, what's math and what's programming sometimes. Do people generally have some programming experience, or is that common or not? I don't know.
Usually we have programming in school and different languages as usual.
Okay. What about like with understanding algorithms from that perspective? Okay. So programming itself, this isn't going to be, anything that'll have a new problem, but what's of more interest and can sometimes actually be accessible is an algorithm. It's coming up with some sort of algorithm or doing some improvement. So what happens, what computer scientists do to look at how efficient an algorithm is, I'll use sorting as an example. Would they talk about sorting in their programming classes?
Yes, for example, in the Junior Academy of Science, we have a course with some basic algorithm like sorting or something like this. So all our audience have opportunity to have such kind of courses just in our department, our laboratory.
Okay, good. So this is something where, in all fairness, I think that there are more opportunities. Every decade you go back, maybe there's some lower hanging fruit, or maybe there's some new stuff to look at too. So, the way we measure the efficiency, there's a couple ways of measuring the efficiency of an algorithm. One of them, maybe you have some very restricted use case and you're even counting computer cycles and, how many cycles it takes to do this, this, and this. But usually what we talk about is, for the complexity of an algorithm, is for when you have bigger and bigger and bigger data. So take sorting, for example. Let's say that I'm teaching some class, and this is just kind of a real world example. I'm teaching some class and I have a stack of papers I need to grade. And so I need to, if I have just 10 papers, I want to sort them alphabetically. If I just have 10 papers, then no problem, I can just easily. But what if I have 1,000 papers? It can happen at like a big university that you have some just gigantic classes with many students. Then the actual algorithm you choose makes a really, really big difference. If you use some sort of very simple algorithm, maybe you literally have to do something like 500,000 tasks to sort these, or like 1 million, something like that. This is if like the number of steps you do is related to the square of the number of papers. But what if you just have, if you're doing some more efficient algorithm, then maybe you only have like a couple thousand things to do. And that disparity, that difference between these only grows as you have bigger and bigger stacks. So this example with sorting, this is something that's a known problem. This is given in any basic computer science class. So it's not something you're going to really make any, for sure, you're not going to make any improvements on this. But there are all kinds of algorithms to do who knows what, and you see these everywhere in life. You see Google Maps, you want to go around Kiev, for example, or Kyiv. I'm having a hard time pronouncing it the Ukrainian way. This is an American.
Kyiv. In Ukraine, it's Kyiv.
Kyiv.
Yes.
Yeah. Okay. I'm going to accidentally say Kiev many times. I'll try to say Kyiv. Sorry, this is very difficult. Yeah. So anyways, let's say the biggest city in Ukraine. And, there's some algorithm that it chooses to optimize your route. And of course, it's often not even fully the best route if you know the city better than Google, or sometimes it comes up with something better than what you can think of. So all these types of tasks, you can think about all kinds of daily tasks of, where things can be optimized a bit more. So this also relates to an area called I'll just type it like combinatorics, for example. combinatorics, and let's say / graph theory. So a lot of computer algorithms are operating on some graphs, and it's kind of informally, I don't know if they studied graphs, but you can think of it as some nodes and some connections between the nodes, sometimes with the weighting. So like a very simple version of something like Google Maps, you may have like intersections of streets and some weighting on the street that says how long the street is or how many minutes it should take to go across it. And you know, the actual algorithms Google uses are, of course, much more complicated. But that's just an example of, you know, you can look and find what are some algorithms that may be used in daily life, give your own take on it, or even just kind of look at some of these problems in graph theory. Like there was a summer math camp in the Detroit area for high school students I used to go to. And the guy who's running it now is in combinatorics and graph theory, you know, this side of math. And he's had very, very good success working with some very smart high school students to produce some new results in this area. And he's someone who's an expert in this. I am not. So I can definitely not tell you what to look at there. But there are, you know, people who might know. And I would say not to be afraid to write someone in a polite way. You know, that they might not respond, but who cares? You know, they're not going to remember if they don't respond.
In our laboratory, we have a guy who worked in Google, and now he teaching programming and all you said about combinatorics, algorithm, and graph theory. And for example, the lecture before you, he told us about, for example, modeling of COVID, propagation, pandemic, like in graph theory. So it's absolutely the same you talk now, so it's okay. We have so opportunity.
Yeah. Hopefully everyone believes now that there's two people saying the same thing. You know, that can help sometimes.
Yes.
Okay, good. So maybe you know, talk to that. He's Ukrainian.
Yes. Okay. He works in our laboratory, so it's for our audience. So
okay. So first suggestion: talk to that guy. So that could be useful.
Yeah.
Don't tell him I told you to harass him, but probably it's good to talk to him. Another point in general, and this is something that I also have to emphasize in terms of, you know, doing math. You know, you hear all these romantic stories from hundreds of years ago about some, you know, 13-year-old kid who was really smart and came up with some nice idea, and it's, you know, still has his name today and all this. And that's not the reality in 2021 anymore. Like the people that are living today are just as smart as, and probably smarter than the people who lived ago. The problem is that math is just more developed, and these types of things, you can't grab them anymore. So just don't even think about this. The other thing too, and this was something that was hard for me and maybe for some of you when I was younger, talking to other people and working with other people is actually very important. Math is a very social activity. There's certain romanticism of sitting in your basement working on some brilliant theory. It's nonsense. That has happened. I don't want to say that it can't happen. You know, there's like, you can even take one of the examples, Grigori Perelman, right? He was the one who proved the Poincare conjecture. So he was famous. Some years ago, he resolved the only Millennial Prize problem that's ever been resolved. So you get $1 million US if you solve one of these 7 problems. And trust me, that this is the hardest possible way to make $1 million. That should not be your motivation to do this. It'd be much easier to do anything else to get that money. But he was a very, very smart guy and also very eccentric. And he, you know, solved this problem on his own, but not really, because the way mathematics works is everyone builds on each other's work. So he had the last piece of the puzzle. And like I said, he was kind of an eccentric guy, and he was irritated that he got all the credit for it. So he thought that, okay, not just him, but all these other people should also be getting credit. And he did something I would never do, and he turned down the $1 million. Nobody do that. You know, if someone gives you $1 million, you take it. But he turned down the $1 million. He turned down the prize. He turned down the Fields Medal and all these things that. So even though one could point to this being a case of someone working on their own, he was still publishing other papers. He was already known for some other results he'd proved. he was still going to conferences, collaborating and discussing things with other people. Just because he put the final kind of, icing on the cake, that doesn't mean that he was working by himself. And any example you find of this in the modern day, where someone supposedly was working by themselves and is given a lot of credits, not exactly. They're part of this social matrix that you call, the mathematical community. And I want to just emphasize that this is just kind of good advice anyways for, mathematics, that if you have a hard time accepting, you need to hear and accept this as soon as possible, that the mathematical community, it's very important to be able to network, to socialize, to do whatever sort of political stuff, just to make the right connections. And it will, working with others who are, will actually contribute good ideas is very, very, very important. So being social, important, that matters a lot. And also in the sciences as well. So for other problems, like I'll give my area of math actually has things that are accessible to younger students, but not without a lot of initial investments. So like I mentioned that I published some papers, one with a 15-year-old, and then the guy who's 16 that I published a paper with, we've now written more than 10 papers, and he's at Princeton at the moment. So we continue to work, and we've had some, very nice collaborations. So my area, but I want to emphasize, he was a great success, but it's not just that he was a smart guy, and he definitely was a smart guy. He's smarter than I am for sure. And, but it's that he was willing to take advantage of an opportunity that was presented to him. So I was meeting with him every other day for 3 hours. So we would talk math for 3 hours. Then he would go back and he'd work and work and work and work. And then he'd have ideas and questions, and he'd come to me, and then we'd talk for 3 hours, and it would keep going like this. And then after some amount of time of this, then he was ready to start thinking about some questions. So there are some parts of math where there's kind of an investment, and it's almost like an apprenticeship. Some hundreds of years ago, you would have like a blacksmith, as an apprentice. The people, I don't know what blacksmith is in Ukrainian. Would they know this word? I think your microphone's muted.
Oh. Yes, I think it's кузнець, да? На українською я не знаю, російською. Коваль.
Yeah, я не знаю, I don't know. Yeah. So I can understand a decent amount. So, yeah, so like this is an example of, traditionally what would happen is it's not a matter of taking classes, it's a matter of having some sort of mentor that you're learning under. And math, it's the exact same sort of thing. I mean, you're also taking classes, and that's important. But the important thing is, finding someone who's willing to talk to you and kind of help you through some things. And so that's what I did with these kids. Is, we found, and I want to say this area of math, let me just very vaguely state what we're looking at is it's something called a normal number. And I'll type this because you can Google it. And once again, I apologize for not having slides, but just the circumstances were really, really crazy. So you can Google, normal number, and the Wikipedia page is not the best resource because it's too hard. But roughly speaking, a normal number is one whose decimal expansion is random. Okay. So you see a 7, 1 in 10 times, you see a 5 followed by an 8, 1 in 100 times, and so on and so on.
So P, about pi is normal or not? Now it's a question.
Yeah, did we discuss that or not? I forget if we talked about that.
No,
okay, well that's a very
I know that problem.
Okay, so you've heard of this problem before.
Yeah.
Yeah, the question of whether that's an interesting one to bring up. Is pi normal or not? I think that's going to take a few hundred years before anybody knows. Probably it is. Probably it's normal in every base. But this is actually a good example of this difference between science and mathematics, because you can compute. I don't know if anyone knows how many digits of pi have been computed. I don't know.
Its number increased each year, each month.
Yeah, yeah. So there's people that for whatever, there are some motivations. I think mostly it's just kind of fun, but people compute these digits of pi and you can do all these statistical tests. And it looks like pi is probably, any base you were to compute it in, it looks like it's probably normal, but we don't know that, okay, maybe after a Google digits of pi, maybe it's only 5s and 7s, right? Maybe nobody knows. Here's how little we know about the decimal or any base expansion of pi. We don't know any example of a digit that occurs infinitely often. Are there infinitely many 5s in the decimal expansion of pi? Nobody knows. And here's the problem, that you get these like memes on Facebook saying that like everything that's ever been written is in the digits of pi. And this is just complete, for lack of a more polite word, bullshit, because nobody knows. Probably that's the case, but that's the, basically that claim, it's something weaker than being normal. It's that everything is there at least once. And nobody knows. Like this itself is probably already enough to get you a Fields Medal if you can show that. It's that hard. And so the easiest example of a normal number, I'll type this. This is Champernowne number, and this is from 1933. And I gave another talk earlier today in Montenegro, and I was just talking about some of this stuff. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, ... 99, 100, 101, ... 999, 1000, ... So the ... meaning continue the pattern. So you take all the natural numbers and you write them in order and you concatenate their digits. And the claim is that this real number is normal in base 10. Now, that's not obvious. So if anyone can prove this, you might know enough to prove it. In fact, it's the sort of thing like the amount of knowledge required to prove this is very, very little, but it's tricky. So it's kind of like, some of these Olympiad problems, right? That like, maybe they only use something very simple, but probably no one, almost nobody can actually solve a lot of these problems. So it's a difficult question. If anyone thinks they have a solution, please email me. This is something I'll do in like my classes. If I have like a younger, very enthusiastic and smart student who has just tons of energy and thinks he or she can do anything, I give this question, and almost always it stops them in their tracks. But they can get a little progress in this. So that's a good question, where we can get a little progress but can't finish it. But studying these objects, there are actually some interesting questions involving these types of numbers, but there's an investment required. So if someone happens to be, I don't know, in Poznan, Poland for a little while, where I live, I'd be happy to discuss these. It's probably wouldn't work well online, but that's one example of something that's somewhat accessible, but requires a lot of dedication. Some other areas of math, there is no chance whatsoever. Don't even think about it. There's some areas of math that are very abstract. Now, when I say don't think about it, like there is an occasional high school student who's very, very talented and very dedicated that can prove some result in a very abstract and hard area of math. I don't want to say it's impossible. Every year there's someone like this, but I don't know who's in the audience here, so that the chances generally are very low. Like if we have any IMO gold medalists in the audience, then knock yourself out, go ahead, try it. But short of that,
could the problems from the Olympiads be the source for a research problem, or it's impossible? What do you think?
Sometimes yes, actually. So this is the thing. Okay, so some people criticize Olympiads as like, that's not real math. The conditions are not how you actually do math. You're not working together. You're under time conditions. And honestly, these criticisms are correct. However, I've seen many Olympiad problems that now that I know more math, I know where they come from. And it's like, I know for sure some Putnam problems. I don't know if you guys play with Putnam problems, because those can be fun too. So do you know what the Putnam is?
No.
Okay.
Could you explain?
Yeah, so the Putnam, it's the big exam for undergrad, not high school students, but undergraduate students like in the US and Canada.
Yeah.
And so it is sometimes somewhat of a battleground for students who, did the International Math Olympiad before, and then they go to university, top universities in the US, and then take this thing. And so it, is also very difficult and very competitive. One of the differences is that anybody can take the Putnam, so there's no requirements to take it. Granted, of course, the people who are taking it, usually there's a reason they decide to take it, but it's very difficult, and some of the questions are very interesting. So there was one some year ago. It was something like the following. Let me try to type it. It's I'm gonna type something a little different than what the question was, but this was related to something that I think was a Putnam problem and actually can be perturbed to ask a lot of very interesting questions. Prove that.
Could you type the name so maybe we could try further to Google about this exam and about...
I can type something that might give some, unfortunately, too advanced search results, but maybe you can get something. So let's say the phrase something like irrational circle rotations. And actually, this is related to something that I was attempting to do as research when I was a high school student. So what you can do is you can look at, I'm going to use fractional, FRACT part of X. So for example, of 1.4421 ... is equal to 0.4142. Okay. So you just take off the integer part, you take whatever after the decimal point. So let me give an exercise that's to students here, exercise, and I think this was like maybe one of the easier Putnam problems at one point. I don't know. Something similar to this. Exercise would be as follows. If X is irrational, then the sequence, let's say n times X is dense in 0, 1. Now,
that was the problem on exam?
Yeah. I'm not sure if it wasn't, but something similar to this was.
Okay. Yep.
Do you see how to do it or not?
And what, how many time does it take?
Well, I mean, this was, I think, one of the easier of many, there are many harder ones. So at the Putnam, you have 6 hours, but there's 12 questions, and some of them are brutally difficult. I'm not sure that this was on the Putnam, but something similar related to this was. There are some very, very hard problems if you perturb this. Like if you change that to n squared, then I can bet that no one here knows how to do it. If it's just n, then maybe someone will come up with an idea, but n squared, it becomes extremely difficult. I know how I can say how to do it. There's a certain trick, but anyways, these types of sequence start leading into an area of research called ergodic theory. And please, nobody actually try to do any research in ergodic theory because you need to know a lot to get started, but you can Google this. It's a very hot area of mathematics right now. And also, Terence Tao, who many people say is the best mathematician in the world at the moment. He's done a lot of interesting stuff with ergodic theory.
Fractal geometry, so it's so beautiful. Is there any sense to do something in fractals?
There can be. So these sorts of things, yeah, I mean, that's an interesting one you bring up. It depends. I would say in some ways that can maybe be more of like a computer or applied type of thing than, okay, like the actual like real, fractal geometry is a very interesting and difficult area and beautiful area of theoretical math. So, understanding, for example, what is the definition of Hausdorff dimension, it's somewhat abstract. So there's fractals you can assign, there's all kinds of different dimensions you can assign. I could see, yeah, I mean, there's possibly something you could do. You know, a lot of people have probably already done projects with fractals for starters, but I would say there are a lot of, I hate to be too, you know, let's say uninteresting things you can do with fractals without knowing much. And it depends on really what you want to actually do. So if you want something, you know, if you can have plenty of pretty pictures, you know, fractals appear everywhere in nature. You know, even you look at like a tree or your cardiovascular system or anything, and there's some fractal structure. And there could be some sort of, I would say not that interesting, but at least of some substance kind of project you could do. Maybe where you just find interesting examples of where fractals are around. Like I said, I don't think that that's necessarily so novel or interesting, but there could be something along these lines. You know, fractals do appear in some very strange and surprising places. So there are, like, if we're talking about like applied math or mathematical modeling, there are applications of fractal geometry even in biology. So for example, like cancer, there's something called a box dimension. It's a measure, it's one of the dimensions of a fractal. So like the actual main dimension, Hausdorff dimension that people use to call, you know, fractals, you can't really do anything with a computer to really do a very good job of giving you an estimate. But box dimension, you can. There are some algorithms you can use. So I'll just type these because we have like Hausdorff dimension and then also box dimension. So there's some, I know there's some research, I don't know too much about it, you'd have to ask someone else, but where something about the box dimension of some structures that like might be cancer cells can maybe be used to diagnose, is this cancer, is it dangerous? It kind of gives an idea of like how much chaos and how many things have gone wrong. So if the structure is more regular, then maybe it's more of a healthy cell. So when I say about like finding things in nature that have some sort of fractal structure, there are some actually very deep and very important things to be done. It's just realistically in terms of what can be just kind of more like a, you know, look, this is fun stuff versus like something that's, you know, there's like, I think kind of a big gap between the two, unfortunately. And that's kind of the problem here, is getting something that's not just totally silly and uninteresting versus something that's actually really deep. Like this gap between them is really hard. So ideally you want something in the middle so it can at least say you did something, but then you don't want something too hard. So so this is one thing also I just want to emphasize about research, is like there is a high probability of failure. You got to realize this. Like as a mathematician, I am, you know, you might think, okay, someone who's professional mathematician has written a lot of papers, has a lot of results, you know, is always on top of their game and knows what they're doing. And most of the time I'm confused. Most of the time I'm banging my head on the table. I don't know what's going on, or I thought I knew what I was doing, and then it turns out I don't, and I'm discouraged and depressed and need to, you know, get my energy back and okay, attack it again. And then maybe I saved something, maybe I didn't, maybe I just had completely the wrong idea. So this is something I would also say in terms of theoretical math, that there's a certain amount of emotional fortitude that's required. You know, it's, I think also for experimental sciences as well, that, you know, there's
the same. I think the same
yeah.
situation. So yeah. you have some hypothesis, and then you fail when you check it, and the state you already mentioned, it's normal for all scientists, I think.
That's true. Yeah, I think you're right. I think it's like kind of, I would say it's different, but kind of the same category. So yeah, you have, and you know, in science, you have your lab work. One of the things is you're not waiting for an experiment to finish. You know, you can probably pretty much do whatever you want if you have some books, your laptop, a piece of paper, and a pen or pencil. So, I mean, honestly, I'm doing most of my work like from a coffee shop or wherever. You know, I'm not in my office or whatever. You know, and that's the difference in science. You often need some equipment depending what you're doing. But yeah, there's a lot of frustration going into research, and that's one way where it's, you know, hard as a younger person. I mean, just being honest, I would say it's more useful probably at your stage to learn math than to try to do it. You know, that's, I mean, I know, you know, I shouldn't say things to discourage from the thing I'm saying how
but this is an adventure. So when you
is,
are in this adventure, you're also studying and I think
Mm-hmm.
it's right way to make research.
Yeah, as long as you don't set your expectations too high, you know, it's because it can happen. But so this is where I was saying, even with some of these like really hard open problems, that it's fun to play with for an hour and just kind of see, okay, well, I just don't know what to do. When you actually start dedicating real amount of time to it, you know, it's so so basically, like, just kind of to summarize this, finding someone to talk to is really, really important. You know, maybe this guy that talked to you before, he could, you know, if you're interested in things with graphs and others, you can talk to him. There can be other areas of math where there are problems, but you definitely should run it by someone, because this is what happened to me when I was a high school student. There were some problems that I was trying to solve, and unfortunately, there was no one around me that really knew anything about math. And there was some stuff that I later found just by taking an undergraduate class that I was trying to do that was literally impossible, that was provably impossible. So you can sometimes run into some obstruction that, you know, maybe someone a few hundred years ago showed, like, okay, there's this reason why this is actually not just hard to do, but literally impossible to do. And ideally, someone who's experienced can say, like, oh, yeah, that looks interesting, but there's this thing that you just haven't learned yet that says that you can't do that. So this can save you a lot of energy just kind of going nowhere. So I want to emphasize that as important. Also, of course, you know, other people don't necessarily know, you know, it's, you know, okay, you know, if I'm going to have, say, a PhD student, you know, I'm going to be trying to give them a problem that I think is probably doable. But the problem is, unless you actually sit down and work things out yourself, there might be some obstruction you didn't anticipate. So even if you run into some, you know, famous professor who says, okay, this should be doable, he might still be wrong, even if he knows very well what he's doing. So this is where, you know, you also need some sort of confidence to kind of bring things up when it, you know, seems that they're wrong. So just because, you know, I'll just say it right now, just because someone's a famous mathematician and is, you know, maybe very smart or experienced, okay, maybe he or she is more likely to know things than you, but that doesn't mean that they're always going to know things that, you know, that they're going to know more than you on something. And I think this is something some people have a hard time with. And I think especially maybe even in the way things are done, I think in, like, you know, some Eastern European countries where I think the kind of authority structure can be a little more intimidating. I think in the US, it's not quite as bad with this. I noticed this from, like, both, like, professors from former Soviet bloc countries, that a lot of them kind of had this sort of scary sort of way of doing things. My PhD advisor was from Ukraine, and he was always very, he was from Kiev, Vitaly Bergolsin. So he was born in Kiev. So, and I'm not sure, like, I think he was born, grew up there, and then he lived somewhere else. Then he moved to Israel, and I don't know the whole situation, but I definitely have experience in the US with professors from, you know, this region, and they're often some of the more scarier ones, at least when you're a student. So.
And have been, yes, such problems of scientific mentoring, because as we understand, and you mentioned that it's difficult to do research work without a good mentor. Yeah. So did you hear about some programs, or maybe in the EU, and how they organized? Maybe you have some information about this one, because junior academia of science, it's about research work, and research work should be supported by mentors. And now we're thinking about how to do it regularly, or because we have the same situation. So some high students wants to make a research work, and they should find to write down and said, please, I have a questions to somebody, but it's a little bit chaotic. But I think the aim of junior academia of science to make it regularly. And have you got any maybe information? Or
in terms of the EU, I honestly don't know. In terms of the United States, I do know. So this is more aimed at undergraduates and high school students. So there is a big push in the United States for undergraduate mathematical research. And okay, this is part of what I was saying about this issue with barrier to entry, right? It's lower for, that doesn't mean sciences are any better or worse than math. It's just there's, the difference is that there's a lower barrier to entry, so you can start doing experiments before you can really start doing, theoretical proofs. And so there is this push for undergraduate research that makes more sense, in my opinion, for, sciences, let's say biology, chemistry, social sciences. Like I remember I was also studying psychology when I was an undergraduate, and even in, taking undergraduate classes, I could read psychology research papers. Taking undergraduate math classes, that's not enough to read math research papers. So this is kind of what I mean about the barrier to entry sort of problem. So in the United States, there is a push for undergraduate research. There is a science fair for high school research, but I think I think there's, less funds and less of a serious, it's not as pushed for as much. So there are things called, I'll type it here, but remember, this is the US, REU. So this is something that research experience for undergraduates is what it stands for. And this is in the US and for when you're an undergraduate, and you can apply for these. And sometimes there's a positive outcome with these experiences, but I actually never did one myself. And I know some people who've done one, some who haven't. The most important thing, I think, is to find someone, that you're comfortable with to work with. And let me also emphasize another thing too that's really important, that when you're working with someone as a mentor, it's not just a matter of, their credentials or what they know. It's also a big importance that, your personalities match as well. Like, I really can't, emphasize that enough. That it's because like if you're just clashing and just do not like each other at all, then that really affects how things go. This is getting back to, math being a social activity. So that doesn't mean that like you're hanging out with them doing whatever, but just that you can kind of work in a reasonable sort of way. And one of the ways this can even be very different. Like, some students are very independent, and some mentors want to control every single detail. And for some students that works great. So like honestly, like as a mentor, I'm actually much better if I can control pretty much what the student is doing. But I'm fine if the student wants to be more independent, I allow that. But my effectiveness goes down, unfortunately. And I think there might be some other mentors who work differently. So as a student, I'm very independent. So I would actually probably do a very bad job mentoring myself. But I think I can mentor other people with, this sort of other type of personality that's not my personality. So that's something that's kind of important as well. And you don't really know it's going to be a good match. So I don't know that I have like an algorithm to suggest how to resolve that, but it is important. Same thing with PhD advisors as well, if you go on to get a doctorate. But also, this is also where some amount of confidence comes in. So my dad, his PhD is in chemistry. And so I remember he told me that his advisor was having him do all these experiments that my dad knew would not work. But the advisor kept saying, do it again, do it again. My dad knew for sure it's not going to work. And then the advisor just ran off to Germany for 2 years. And so basically, that was in a sense neglectful as an advisor. But my dad, like me, was independent enough that he's like, okay, well, now I can just do whatever I want. And then he had amazing results. And then I think he got offered a postdoc at MIT. So, because the research went really, really, really well. Like, in my situation, I didn't talk to my PhD advisor other than an occasional email the last 2 years of my PhD, 2 or 3 years of my PhD. It was just more effective for me just to kind of think about things on my own and work them out. But he at least got me started kind of in the right direction. And then once I had that kind of little bit just to latch onto, then I could kind of go from there. Other people really need their hands held a lot, and that there's nothing wrong with that. So that's important as well. There's other stuff you maybe wanted to bring up. I know I'm just kind of talking about a lot of various things, but was there anything, Katerina, was there anything else you wanted to bring up?
Maybe we have already 1 hour left.
Yeah.
I think maybe we have some questions from our audience. Тобто ви можете написати ваше запитання, можете написати українською, я буду намагатись перекладати, або можете включити ваш мікрофончик і запитати, поставити запитання. because I think it's quite interesting. Maybe most of my question about maybe education in United States, about mathematics in United States, about maybe the level of math in United States, but
and hopefully it's clear. I'm going to give everyone an honest answer, you know, if someone asks. So if something is bad, I'll say it. And if it's good, I'll say it. So this is your chance. If you really want to know how things actually are, please ask.
So I think now everybody's sleeping, already sleeping.
But late at night in Ukraine or something. That's
it's 7 o'clock.
Yeah,
so it's normal time.
It's only 6 o'clock in Montenegro. So, so were there any other questions? I mean, I know that this doesn't give you like an algorithm. I mean, part of this solution, it's not really. It's hard, you know. That's the thing. Like, there's no clear way to get a good problem. Like, I wish I could say there was, but
yes, you show us the waves where we're not going to go. So
that's important. Yeah, as well.
It's usually like negative result from your scientific research. I don't know why we could not publish, because sometimes you could work 1 year and with a negative results and you couldn't publish it.
Well, yeah, and that's a valid criticism of science, that, you know, you were getting incorrect, not reproducible results because people are trying to get a positive result where there is none, and that's, you know, a weakness of science as a, you know, social side of it. So
we should change something, because I know in math it's not a problem, but for example in biotech they have a lot of not reproducible results because of cherry picking, because they push to publish or perish. That's why we have lots of problem in science. So but in mathematics and physics I think these fields are safe.
Physics, I don't even know. Like in physics, there's still some room for this, at least. For
for experiments.
I think there's more in biology, but still.
For cherry picking, but now we have lots of mechanism. For example, when we have numerical modeling, we should attach, for example, lots of files, maybe input files, output files to reproduce. So we have a lot of mechanisms now to avoid this problem I mentioned. So I think no questions. I think all my questions I already asked you, and maybe that's time to say you thank you very much for your talk. And you're so enthusiastic, and I want to wish you to have lots of talented and brilliant students, and hopefully next year you will visit Ukraine, and we could invite you to soon we will have a museum of mathematics.
Oh, good.
Yes, I think in the end of the spring or in the summer. Definitely in the summer we will have a museum of mathematics, and we will have lots of space for lectures, and I hope we will see and meet with you in our museum.
That would be great. Summer is more likely, but I don't know. There's a good chance we'll be back at some point. So
summer or autumn. I hope in summer it will be already done. But not in spring, because I think spring it's a question, but in the summer I think it will be, and then in autumn or in winter, next winter, I think without COVID, and we have lots of space and very nice modern space for invited lecture. So I hope to see you there.
Yeah, I'm sure I will. I think I've already been to Ukraine like 13 or 14 times already. I forget. So it's a lot. So I'm sure there'll be another time at some point. So
there wasn't Museum of Math that time.
Yeah, there was not a Museum of Math.
Yes, because it will be the point of attraction for all people who likes math, like you, like our audience. So
So there's, I know, по-русски до свидания, is it до побачення? По-українськи?
До побачення.
Побачення.
It's like it's до видения. Yes, it's closer to Polish.
Yeah. So I'll just say do widzenia, because I don't know more people. or whatever. So
hey, have a nice evening.
All right. All right. Thank you. All right. Bye.
Bye. Thanks for lection.